Abicon tutorial.
Good day, listeners. Today we are solving a variable coefficient differential equation by Adomian Decomposition Method. And the differential equation is as shown on the screen. Y prime prime plus xy prime plus y squared equal to x. The initial conditions are y of 0 equal to 0, y prime of 0 equal to 1. So as usual for ADM, so we first of all express the differential equation in operator form. In an operator form, our differential equation becomes Ly equal to x minus xy prime minus y squared. So the operator for this differential equation is a second order one, and we assume that the inverse operator exists. The operator is Ly equal to the square, the x squared, and then the inverse operator is of the form this dx. So applying the inverse operator on the operator form of the differential equation, we have this equal to L inverse of x minus L inverse of xy prime minus L inverse of y squared. And then this one becomes y of x equal to L inverse of x minus L inverse of xy prime minus L inverse of y squared. At this stage now, we want to apply the initial conditions. So the initial conditions are applied. These are the initial conditions. So they are applied as y of 0 plus x y prime of 0, then plus L inverse of x minus L inverse of xy prime minus L inverse of y squared. So all these three make up our zeroth term, while the remaining two terms become the recursive relation. So for the zeroth term, we know that this is 0, this is 1. So we have y naught equal to 0 that's from our initial condition given to us. So this becomes x times 1 and then L inverse of x. So y naught becomes x plus, since our L inverse is a second order operator, inverse operator, so integrating it twice will give us x raised to the power 3 over 6. So this is our zeroth term. Then the remaining term can be expressed as a recursive relation in this form, minus L inverse x y n minus L inverse. So for the nonlinear term in Adomian Decomposition Method, we usually decompose it using Adomian polynomials. So in one of our videos, the calculation of Adomian polynomials have been well explained. So listeners can just check one of these videos and then study them. So here, this one is represented as an. So our Adomian can use anything to represent it, either an, bn, or whatever, or any constant that will not confuse us. So it is represented as an here, and Adomian decomposition for y squared, like I said, and explained. So a naught here will be y naught squared. A1 will be 2 y naught y1. So we just go ahead and apply it. So yeah, for this one now, when n So when n is equal to 0, we have y1 equal to L inverse of, this should be prime. Yes, that's prime. So L inverse x prime naught minus L inverse a naught. Then furthermore, this can be written as minus L inverse x y naught prime minus L inverse our a naught by y squared. So by what is written here becomes y naught squared. So here y naught square is going to be x plus x raised to the power 3 all square, and if we expand this, we will obtain x raised to the power 4 over 3 plus x raised to the power 6 over 36. So that's our y naught. So we have obtained our y naught squared. Then let's obtain our y naught prime. We should not forget that this is our y naught, which is needed here. So differentiating it once, y naught prime will give us 1 plus x squared over 2. So we plug in y naught prime here and then y naught squared into this. So our y1 will now become minus L inverse of x into 1 plus x squared over 2, then minus L inverse of our Adomian polynomial, decomposed Adomian polynomial, which is x squared plus x raised to the power 4 over 3 plus x raised to the power 6 over 36. We should not forget that our L inverse is a second order inverse operator. So that means we are integrating twice. But before we do that, so we have this written as x plus x raised to the power 3 over 2. And then this is L inverse x squared plus x raised to the power 4 over 3 plus x raised to the power 6 over 36. So finally, to obtain y1, our y1 will now be minus integral, double integral, x plus x raised to the power 3 over 2 dx minus double integral x squared plus x raised to the power 4 over 3 plus x raised to the power 6 over 36 dx, and doing that will now give us y1. So when that is integrated twice and then simplified, we obtain x raised to the power 3 over 6 minus x raised to the power 4 over 12 minus x raised to the power 5 over 40 minus x raised to the power 6 over 90 minus x raised to the power 8 over 2016. So this is y1. Of course, as a result of the type of zeroth term we have, the computation will become bulky, and so of course there are modified way of doing that. So but for this, we have y1 obtained here. So, and this is where we're going to end the computation. So we can then say y of x becomes y naught plus y1. Like I said, we can still obtain more terms. So with that, from our y naught, which is x minus x plus x raised to power 3 over 6, then we'll have minus x raised to power 3 over 6 minus x raised to power 4 over 12 minus x raised to power 5 over 40 minus x raised to power 6 over 90 minus x raised to power 8 over 2016. So simplifying this will give us a truncated series of the solution. So x minus x raised to power 4 over 12 minus x raised to power 5 over 40 minus x raised to power 6 over 90 minus x raised to power 8 over 2016. If more terms are obtained, we will discover that some terms would cancel out as we proceed. Thank you for listening.